The pipe method connects one stream to one other stream. But real applications often need more complex topologies. What if you need to pipe one readable into two writables simultaneously? Or combine multiple readables into a single pipeline? These are the piping patterns the book explores in Chapter 6 final section. Forking is the simpler of the two. You want to take one source of data and send it to two destinations at once. The classic example, generate both an MD5 and a SHA1 checksum of a file in a single pass, rather than reading the file twice. The approach is straightforward: pipe the readable into two separate writable streams. Both receive every chunk. Each writes its output independently. You finish when both are done. The subtlety is error handling. If you use the simple pipe method, an error in one destination does not automatically clean up the other. The book recommends the pipeline utility from the stream module imported from stream/promises in modern Node.js, which properly propagates errors and ensures all streams in the pipeline are destroyed cleanly when something goes wrong. Combining works in the opposite direction. You take multiple separate stream components and present them as a single unified stream. Imagine you want to expose a compress and encrypt capability as if it were one stream. Internally it's a chain, a gzip transform piped to a cipher transform, but to the outside world it looks like one unit you can pipe into and out of. The book implements this as a combined stream: write to the first stage, read from the last stage. The combined stream object handles the internal plumbing and exposes a single interface. This composability, forking, combining, chaining, is what makes stream-based architecture feel like building with a system of interchangeable parts. Forking sends one stream to many destinations. Merging is the reverse: combine multiple readable streams into one. Picture this: you have 3 log files from 3 different servers. You want to process them as a unified stream, merge all the lines together, perhaps sort or analyze them, then write to a single output. Reading each file separately and concatenating would work, but merging as streams means you can start processing before any individual file is fully read. The approach uses a readable in paused mode as the output. You attach data event listeners to each source stream and push each arriving chunk into the merged output. You track how many sources are still active. When all of them emit the end event, you push null to signal the merged stream is done. There's an ordering property worth noting: unlike a sequential concatenation, a merged stream interleaves chunks from all sources in arrival order. If file A and file B produce chunks at the same time, they might be interleaved in the merged output. This is fine for many applications, log aggregation, metrics gathering, but not for applications requiring strict per-source ordering. The book shows merging used in a practical context: merging multiple text files, where chunks from all files flow into a single output stream as they arrive. Each source processes independently, and the merged stream simply collects everything. Error handling in merged streams requires care. An error in any source stream should terminate the merge. Using the pipeline utility again helps here. It provides a clean way to set up the merge with proper error propagation. Merging feeds naturally into the final and most sophisticated piping pattern, multiplexing and demultiplexing. Here's a scenario that appears in distributed systems. You have 2 streams of data, standard output and standard error, from a child process, and you need to send both through a single channel, like a network socket or a file. On the other end, you need to split them back apart. This is multiplexing, combining multiple logical channels into one physical channel. Demultiplexing is the reverse, splitting one physical channel back into multiple logical ones. A naively merged stream loses the channel identity. You can't tell which bytes came from stout and which came from stare. Multiplexing solves this by prefixing each chunk with a header that identifies the channel and states the chunk length. The book implements a simple protocol. Each multiplex chunk has a header, 1 byte for channel ID, 4 bytes for the chunk length as a 32-bit integer, then the chunk data. The muxer reads from both stout and stare, wraps each chunk with this header, and writes to the single output. The demuxer on the other end reads headers, extracts channel ID and length, reads exactly that many bytes of data, and routes them to the appropriate output stream. The result is a remote logging system. A child process on one machine has its stout and stare piped through a multiplex channel to a server, which demultiplexes them back into separate log streams. The elegance here is that the protocol is just a stream transform. The muxer and demuxer are transform streams. They slot into any pipeline. The underlying channel can be a TCP socket, a file, a WebSocket, anything writable. Multiplexing and demultiplexing illustrate a deeper principle. Complex communication protocols can be built from simple stream transforms, composed together with pipe. One of the quietest but most important improvements in modern Node.js stream handling is the pipeline function, now available as a promise from the stream module. Here's the problem it solves. Classic pipe does not handle errors well. If a stream in the middle of a pipeline emits an error, pipe does not automatically destroy the other streams in the pipeline. You can end up with file descriptors that never close, network connections that stay open, and temporary files that never get cleaned up. If you've ever written careful stream error handling in older Node.js code, you know the pattern: listen for error on every individual stream, call destroy on all of them in the error handler, keep track of all the streams in a closure. It's verbose and easy to get wrong. Pipeline, from stream/promises, does all of this for you. You pass the streams as arguments in order: source, transforms, destination, and it returns a promise. If any stream errors, the promise rejects and all other streams in the pipeline are destroyed. If everything completes successfully, the promise resolves. Cleanup is automatic. The book emphasizes pipeline as the modern, correct way to chain streams. The patterns for combining, forking, merging, multiplexing, and demultiplexing all benefit from pipeline's proper error handling. In Node.js 15 and later, you can also use stream.pipeline with async generators as stages, which opens up a whole new way to write stream processing code using plain async/await syntax rather than extending stream classes. This is the practical conclusion of everything in Chapter 6. Streams are powerful, and pipeline is the tool that makes them production safe. Use pipe for simple cases, pipeline for anything that matters.